All right, thanks, Joe, for that great overview of heliophysics. Next up is Dr. Lisa Carnell from our newest science division, the Biological and Physical Sciences Division.
Thank you. Thank you very much. So, very excited to be here today. This is my second time with AGU. Okay, there we go. Better? Okay. Step over here as I'm being instructed. Um, so, this is the second time that I've been with AGU, and I'm really excited to share because at the core of who the biological and physical sciences is really this thrust area, thriving in space. Everything that we do is enabling NASA to go farther and stay longer and thrive in deep space. So we focus on the changes that happen to not just biology, but physical systems in the spaceflight environment and how that phenomena is changed in spaceflight under various different conditions. It could be radiation, altered gravity environments, and the environment itself, whether it's lunar dust, CO2 changes in the atmosphere. And so we focus on all of these different attributes that are going to be necessary for NASA as we take those next steps with Artemis and Moon to Mars. And we recently received, last year, our decadal survey, and it was asking us to really lean in on how we adapt to space, how we live and thrive in space, and then exploring that phenomena that's hidden by terrestrial limits like gravity. So today I'm really excited to share with you, we developed 5 goals based on the decadal survey within just this past year to really help us focus in on the priority areas that NASA needs and BPS needs in order to address the missions and enabling exploration. Whoops. There we go. So our first goal is focusing on precision health. And so what does that mean? Here on Earth, I think we could probably assume that means how do you address health that's going to affect me personally? You know, when we all take an aspirin or a Tylenol individually, that effect is going to be different. As we look to what it's going to take for NASA to keep our crew healthy and sustained in a long duration mission, we need to really understand what those impacts are, not just across the board for the crew, but at the very individual level. In the space biology area, we focus on looking at all different types of biology, from microbes to rodents and to human models. And we're really leaning into those 3D human models because from those, we can actually develop individualized models of systems that allow us to probe those, evaluate countermeasures to ameliorate radiation effects, and develop even personalized medical kits for those crew on long duration missions. As you know, we're really limited in supplies. So the more that we can personalize these, we can focus on the right supplies we need for these long duration missions. And I'm very excited to say that we actually have a 3D human tissue model that will be flying on Artemis 2. Space crops. So this is our second goal. And with space crops, we're looking at how do we enable a sustainable presence by ensuring that we have the right nutrients that are needed for our astronauts on long duration missions. So here you can see the astronaut walking up to his greenhouse. What is this going to be? What is this going to look like when we get to the lunar surface and have sustainable presence? Not only are we looking at ways and the right types of cultivars and crops that we should be growing and that are nutrient dense for our crew members, but the technology that's going to be required to actually grow them in the spaceflight environment. We do a lot of this research currently on the International Space Station. We've grown crops of wheat, tomatoes, and all sorts of different lettuce. But here we're trying to focus in on what is the most nutrient dense and what do we need to help supplement some of that food that's going to be needed to keep them sustainable and alive. And the technology, you know, watering something in a reduced gravity environment is not simple. And so we're developing new methods and ways in which we can actually grow crops in these austere type of environments. And what's really fascinating is that all of this information and the data that we're getting from growing crops in space and on the International Space Station, we can translate that to right here on Earth. And so you see a lot of agricultural innovations coming from NASA, like using LED lights or controlled environment agriculture for vertical farming. So this is quite a leap, literally quantum leaps for BPS. We span everything imaginable and all the way down to the quantum level. So here, right now, what is it? We know maybe 5% of what's happening in the universe. And I think you heard Dr. Clampin earlier talking about really trying to understand dark matter, dark energy. And one of our thrusts is to actually eventually go out and make those measurements so we can quantify some of that. And right now we're doing some early stage research on the International Space Station using the Cold Atom Laboratory. And they've been able to actually use atom interferometers to measure and report out the dual Bose-Einstein condensate, rubidium and potassium. And the reason they can do that in space is because not only do they cool them to a level to slow the atoms down, you can do that on Earth, but we are able to do that in a reduced gravity environment that allows those atoms to remain suspended so we can make those measurements. As we all know, the technology that we learn from quantum development impacts our everyday lives, from cell phones, GPS systems, and all sorts of technologies that we have in our everyday use. And foundations. So foundations is kind of everything that we do in the physical sciences arena. So as you can see, we have the combustion over here on the left. Fire safety is absolutely critical. Right now here on Earth is very easy. We have fire extinguishers, we have firefighters and support. We don't even know for sure how flames are going to react and behave once we get to the lunar environment. And so we're actually sending a payload on the uncrewed demo to understand that partial gravity environment and what the higher oxygen concentration can do to fire safety. Looking at initiation, propagation, and then how do we extinguish that in a different environment. And in the middle, you see fluids behavior. Fluids do not behave the same in the spaceflight environment as they do here on the ground. And so understanding how fluid flow happens, as you can see, we have to literally force the water to go into like the plants in order to water crops. You guys have probably seen bubbles floating around on images or videos of space station. Imagine watering your plants in space. The water is just going to be floating around. How do you actually get the water down to the plants? A lot of times we don't think about these really simple aspects. We have our fluids folks, the experts there that are actually working on this to ensure that happens. We're also looking at cryogenic fluid transfer as we need to transfer cryogenic fluids for actually accomplishing the mission and sending the Starship out to space. We need to understand what that cryogenic fluid transfer is going to look like. And on the very far end, I think it's kind of cool. You can see almost like dust particles floating. And that's to represent the materials aspect for the physical sciences. So for materials, we want to focus on make it, don't take it. Because as you know, it's going to be pretty hard and difficult and expensive to send supplies back and forth to the lunar surface or even out to Mars. So how can we take advantage of our in situ resources that are already there, adapt and live, and take advantage of extracting oxygen, or creating a binder so that we can make the bricks and lay the foundation for sustainable presence. And we do all that research right here in the Biological and Physical Sciences Division. And Space Labs. So I'm gonna steal this one, Julie, because Space Labs is literally doing revolutionary research in extraordinary places, because we are doing our research everywhere. And with Space Labs, it could be on the ground using a drop tower. It could be in LEO on these new commercial LEO destinations, out on Gateway, or on the lunar surface, or eventually out to Mars. And so Space Labs covers anywhere we want and need to conduct our research to inform NASA and to have success in enabling exploration missions and long duration. And a really important aspect of Space Labs for BPS, and something we're leaning into that's newer, is called commercially enabled rapid space science. So, we all like the term rapid, right? It would be nice if we could do our science a little bit quicker at times and really get that data back. And we're leaning into Cirrus so that we can actually send our science experiments to the spaceflight environment and have all of it done in situ, analyzed, and the data sent back to us much more rapidly. Rather than right now, we send our experiments up to the International Space Station, wait for the sample to come back to do the analysis, and then maybe send another sample back up. We are going to increase the rate and the pace at which we can do this science and get that data returned back and the benefits back to you and me here on Earth, and not just to NASA, much quicker. And so we're really looking forward to the future of that and the future of the commercial LEO destinations, but also as we move out to the lunar and Mars vicinity. Okay, so with that, I'd like to say thank you for your time and for listening. Again, we in biological and physical sciences, we do all of our research in revolutionary research in extraordinary places. I love that tagline. Thank you, Julie.